This is Lecture 10, Assimilation of Mineral Nutrients. This is part of the plant physiology subject, which is offered as part of the agricultural and viticultural degree programs at NMIT. Please refer to the recommended reading from Tays and Zeiger, Chapter 12 for complementary information. Please ensure that you have watched Topic 4 on nutrients before watching this video. My name is Dr. Nikki Cooley. This lecture on assimilation of mineral nutrients will be separated into two parts. Part 1 will give an overview and definitions of nutrient assimilation, while Part 2 will give quite detailed examples of different mineral assimilations in the plants. Before continuing, it may be wise to give yourself an overview. The following URL link on the slide will enable you to watch a YouTube video which will give an introduction to soil-plant nutrient relationships. This link can be found on Moodle. Higher plants are known as autotrophs, and they synthesize all their organic molecules out of inorganic nutrients. This involves absorption from the soil and incorporation into organic compounds essential for growth. This incorporation of mineral nutrients into substances such as pigments, enzyme cofactors, lipids, nucleic acids, amino acids is all known collectively as nutrient assimilation. The nutrient assimilation is the conversion of nutrients into the fluid or the solid substance of the plant. This process of some nutrients, such as nitrogen and sulfur, is among the most energy-consuming reactions in the living organisms. One such example of assimilation is assimilation of nitrate. Nitrate is a polyatomic ion with the molecular formula NO3-. When plants assimilate nitrate, the nitrogen is converted through a number of intermediates from the NO3-, which is then converted into nitrogen dioxide and then into ammonia. It is converted once more to end up as amino acid glutamate, as shown in the figure on your slide. Nitrogen-fixing bacteria convert molecular nitrogen into ammonia, NH3, which is protonated to form the amino ion NH4+. Assimilation into amino acid consumes about 10 ATPs. The assimilation of sulfate, SO4, 2-, into the amino acid cysteine consumes about 14 ATPs. Enormous energies are involved. If you consider these reactions run rapidly in reverse, they become explosive, releasing vast amounts of energy as motion, heat, and light. Nearly all explosives are based on the rapid oxidation of nitrogen and sulfur compounds. Assimilation of other nutrients involves the formation of complexes with organic compounds. Examples of these are magnesium, which associates with chlorophyll pigments, calcium, which associates with pectins in the cell wall, and molybdenum with enzymes such as nitrogenase. In plant cells, nitrogen is the fourth most abundant element, reflecting its importance. It is found in nucleic acids and amino acids. Most natural and agricultural ecosystems show dynamic increases in productivity following fertilization with nitrogen. Nitrogen is present in vast quantities in the atmosphere, approximately 77%. Mostly not directly available to living organisms. Nitrogen acquisition requires the breaking of exceptionally stable triple covalent bonds. This produces ammonia or nitrate and is called nitrogen fixation. It can be accomplished by industry and natural processes. Industrial nitrogen fixation occurs under high temperatures of 200 degrees C and at high pressures of 200 atmospheres, and in the presence of a metal catalyst ion. nitrogen combines with hydrogen to form ammonia. These extreme conditions are required to overcome the high activation energy of the reaction described by the Haber-Bosch process, the starting point for manufacture of many industrial and agricultural products. In 2009, worldwide industrial production of nitrogen fertilizers was approximately 100 times 10 to the 12 grams per year. That's a lot of fertilizer. The table on your slide, major process of biochemical nitrogen cycle. Review the processes that are available to convert nitrogen to ammonia. This table allows comparisons of the different methods. The rates column in this table illustrate that most nitrogen is fixed by plants, followed by denitrification, where bacteria conversion of nitrate to nitrous oxide and molecular nitrogen is conducted. And then the third most common process is prokaryotic conversion of molecular nitrogen to ammonia. Natural processes which fix nitrogen total approximately 190 times 10 to the 12 grams per year. Lightning is responsible for about 8% of nitrogen fixation. In lightning, it converts water vapour and oxygen into highly reactive hydroxyl-free radicals, free hydrogen atoms and free oxygen atoms, which attack nitrogen to form nitric acid. This falls to the earth with the rain. Photochemical reactions between the gaseous nitrogen nitric oxide and ozone to produce nitric acid account for approximately 2%. Biological nitrogen fixation is where bacteria or blue-green algae, also called cyanobacteria, fix nitrogen into ammonia, which dissolves in water to form ammonium. The figure on your slide from the recommended textbook Tays and Zeiger, figure 2.1, represents a visual illustration of the nitrogen cycle and its components. You can follow the three forms of nitrogen on the slide, where nitrogen is ammonia, or nitrate, or nitrate, or as it's found in the atmosphere as nitrogen. You can see the interconnectedness of how animals and plants fix and use nitrogen, along with the role of the atmosphere and industrial fixation. I will also draw your attention to groundwater leaching, for an overview on the nitrogen cycle, please refer to the YouTube video on the following URL link, which can also be found on Moodle for your convenience. Please watch this. This now brings us to the end of part 1.